So there's a lot of material in thermodynamic relations. We covered a lot last time. Today I'd like to revisit volume expansivity, spend some time on the Joule-Thomson coefficient. Let's go ahead and solve this problem. Partial of T with respect to P holding S constant. We want to do that numerically using data out of the tables for ammonia, and we want to evaluate that derivative at this temperature and that specific volume. That derivative is a partial derivative, and you're holding entropy constant. So think about temperature being a function of pressure and entropy. Make sense? So these be the two independent intensive properties that allow us to fix the state and evaluate other properties like temperature. When you approximate this derivative numerically, think about you need a temperature 2 minus temperature 1. A temperature difference divided by a pressure difference. Isn't that the general formula for df dx or dy dx or d something dt? You know, the change in the numerator over the change in the denominator. This temperature, just think, is a function of pressure and entropy. So it's a function of, let's say, some pressure and entropy. All right? And this other T2, I'm kind of doubling up the subscripts, is a function of some other pressure, P2, comma, S2. Okay? But we have S is equal to a constant. So what do we know about S1 and S2? They're the same. This is the same S, same entropy. Set up a table to help you organize the thing. So think about state 1 and properties. I'll just make a long list of properties. Pressure, you could put it in bar, but I'm going to put it in kilopascal. Temperature, degree C. Specific volume, meters cubed per kilogram. The internal energy, kilojoules per kilogram, which is really not needed, but I want to show you it's just another property. Enthalpy, it's not needed, kilojoules per kilogram, but entropy is needed, kilojoules per kilogram Kelvin. So state 1 and then state 2. State 1, well, what did they tell us? They told us that the temperature was 10 degrees C and the specific volume is 0.44251. So think of that as state 1. I go into the ammonia tables and I look up and I try to evaluate P. Where's P? Can I find P? It's a real challenge to do that because you're not coming in with T or P, you're coming in with T and V. But you can find it, and it's an exact value in a pressure block, the pressure of 300, 3 bar, or 300 kilopascal. You could then look up the value of U. It's right there, 1345.89. It's not needed, but you could look it up. You can look up for the enthalpy, and the entropy is 5.6280. If you have your table, you look it up and see what I'm doing, okay? Now I need to find another state, state 2. What's in common? What do I know about state 2? It's ammonia, yeah. It should be close, because I'm approximating a derivative, it should be close to the other state, state 1. And what's in common? What property value is in common between them? S. So right here, S is equal to 5.6280. I need one other property, right, to sort of fix the state. Now, this is a little bit of a challenge. The tables are set up in pressure blocks because it's superheated ammonia. You could pick a pressure block above it or below it. It's kind of like, I'm just going to pick 350. So that state 2 is by knowing P and S. State 1 was by knowing T and V. Erase this mark here and clean this up a little bit. I know temperature 1, do I not? Do I know pressure 1? 300 kilopascal. Do I know pressure 2? I picked it so it's close and I don't have to do too much interpolation, right? But I need to find T2. How could you find T2? State 2 is fixed by knowing P and S. Set up a little interpolation block on the side, kind of down here. I'll just box it in. The pressure block is all 350. The temperature, you have a temperature at 20 and a temperature at 30. Corresponding entropy of 5.6259 and 5.7057, and the value 5.6280 is right in between those two values. That's why I lifted them out of that pressure block of 350. And so I do an interpolation to find the temperature is 20.26. So right there, I should change the color, put it like this, 20.26. You see that? So that gives me the only other unknown in this derivative. So go ahead and compute the derivative, 20.26 minus the temperature state 1, 10. This was degrees C. Could I substitute Kelvin right now? Sure can. It's a temperature difference. A temperature difference of 1 degree C is exactly the temperature difference of 1 Kelvin. So yes, I can. And now we've put in our pressures. This was 350 minus 300 kilopascal. And so we find the answer, the partial of T with respect to P holding S constant at that state for ammonia is about 0.20526 Kelvin per kilopascal. I throw all those units because that's what your calculator is going to show. And then you're going to say, I need to round off, right? I need to not put that many digits. So you go like this and you say, good, the 3 significant digits. But you know this is a numerical approximation. You could even round it to something like that. You just don't have a lot of confidence in the 3rd digit at all. All right? Box it. There's your answer. That's right, and that's the closest pressure we got. Now you could go 250 or 350 on the pressure, either one. But since I like to do a forward difference for the finite, what we're doing is forward difference for the first derivative approximation. The other one would be backward difference in pressure. And the best would be central difference, but you need a even split above and below. And it would be double the work, but you'd get a better answer. Last time we were introduced to the volume expansivity. And why did I emphasize it in this class? Because you're going to see it again when you cover natural convection and heat transfer. And it talks about how the fluid volume expands as it heats up. We're going to come down and talk about the Joule-Thomson coefficient later, but I wanted to revisit this because this is the way I explained it. But this is the volume expansivity equation is given like this, but you can also express beta as negative 1 over the mass density, partial mass density with respect to temperature at constant pressure, right? The only problem is it's hard for a lot of people to follow the logic. At 4 degrees C, beta is 0 because the derivative of rho with respect to temperature is 0. And then in this region, beta is negative. And in this region, beta is positive. Above 4 degrees C, it's positive. What I did was I went ahead and plotted the specific volume as a function of temperature. You see it's a minimum at 4. And now you can see, oh, it's expanding as I warm it up. And from 4 degrees, if I cool it down some more, it also expands, that's the hard one to grasp. But that's what water does. Water, when you get it very, very cold, and especially when it freezes, it expands on freezing. Most substances, when they go from liquid to solid, freezing, solidification, what do? Contract. Water's very unique. It expands on freezing. So this may be a little easier to see because beta is like, oh yeah, I see it's expanding as the temperature goes up above 4. As well as expanding as it goes lower. You can also just go ahead and calculate the volume expansivity beta as a function of temperature. At around 4 degrees C, the value of beta is 0. At values between 0 and 4, the beta is negative, less than 0. And then the vast majority of the cases, it's positive. And you can see that it grows at 20, 30, 40, 50 degrees C. You can see some numeric values. What are the units on beta? 1 over temperature, typically given in Kelvin. And you can see I had to multiply by 1,000 so that it wasn't so small. So if I wanted to calculate beta, the volume expansivity, for water, or get it out of the table, it would be 0.000458 inverse Kelvin. It doesn't expand that rapidly. Liquid water doesn't expand as rapidly as gases do at constant pressures with increasing temperature. Make sense? Let's now talk about the Joule-Thomson coefficient. So the Joule-Thomson coefficient is defined as how temperature changes with respect to pressure along a line of constant enthalpy or during an isenthalpic process. So this is just a property. That's all the Joule-Thomson coefficient is, just like volume expansivity, specific heats, and other properties. But it's defined in a funny way. How temperature changes as pressure changes for constant enthalpy. What's the application? Throttling processes. So if I have flow going through a throttling valve or a restriction, okay? And I have it well insulated, so Q dot's equal to 0. And I have no work, so W dot's also equal to 0. I can do a control volume analysis, do an energy balance, where I have inlet state 1 coming in at temperature and pressure 1, P1 and T1. It exits at state 2 at P2 and T2. When you do the first law and you neglect changes in kinetic and changes in potential energy, what do you conclude about the property enthalpy in versus enthalpy exit? They're the same. It's an isenthalpic process. Throttling processes, it's adiabatic, negligible changes in kinetic potential energy, it's isenthalpic. True? So if you knew the Joule-Thomson coefficient for this substance undergoing a throttling process, you'd be able to tell right away what is the relationship between the outlet temperature, T2, compared to the inlet temperature. First, what about pressure? P1 versus P2. Is P1 greater than P2, equal to P2, or less than P2? Your intuition is going to have to help you on this one. I have flow through a restriction. It's a throttling device. Can P2 be greater than P1? Can it be equal to P1? Or must it be less than P1? It doesn't make sense any other way. So P1 is greater, true? So it's not like you can let P2 be greater than P1. It doesn't make sense. This is a throttling process. So now what we do is we approximate, so mu sub J, the Joule-Thomson coefficient, is equal to the change in temperature, how about the outlet minus the inlet temperature, divided by the change in pressure, outlet pressure minus the inlet pressure. Did I approximate that derivative okay? And then do a little algebra to say the outlet temperature is equal to the inlet temperature minus the Joule-Thomson coefficient times the inlet pressure minus the outlet pressure. I'm going to pause. I want you to look at that algebra. Give me a thumbs up if you agree I did not make an error, or suggest some correction. You see what I did was I knew that this is a negative delta P right there. P2 is less than P1, so I wanted to get rid of that negative delta P, so I switched P1 minus P2. Make sense? If the Joule-Thomson coefficient's reported to be 0 for this substance, as it undergoes the throttling process, what about the change in temperature? Is the outlet temperature less than T1, equal to T1, or greater than T1? What about the outlet temperature? If the Joule-Thomson coefficient 0, they're equal. See that? I have a pressure drop with no change in temperature. Well, what type of substances could we expect to do that? Liquids, two-phase substances, saturated liquids, saturated vapors, subcooled liquids, superheated vapors. Any substances out there that you can think of where it went through a throttling device, significant pressure drop, the temperature would not change. Do you want time to write down something on your notes and I'd walk around and check it? Or there's a group of substances, a type, okay? And it says if it's this type of substance, even though it undergoes a pressure drop, flow through the restriction, it'll be isothermal. The outlet temperature will not be different than the inlet temperature. What type of substance gives us that behavior? All right, if I say to you, tell me everything you know about the ideal gas model, what are you going to say? You're going to say PV is equal to RT, but you're not going to stop there, are you? You're also going to tell me what? U is a function of temperature only, and enthalpy is a function of temperature only. That's the key right there. For ideal gases, that particular description of fluids, if it undergoes an isenthalpic process, it must also be an isothermal process. So this is for ideal gases, all true ideal gases. Now, let's go on and let's say the Joule-Thomson coefficient's positive. All right? What's that going to do? If this is positive, the pressure change is positive, P1 is greater. I know it's a pressure drop, but P1 is greater than P2. I then subtract off, what do I know about T2? That or that? Is it T2 less than T1? I have a positive Joule-Thomson coefficient. P1 is greater than P2. I have a negative sign sitting right there. There's T1. It's colder when it comes out. It's colder when it comes out. And that happens to most fluids. When we had a refrigerant, we had a restriction. It was very cold when it went through that restriction. True? And then there are some cases, some fluids where the Joule-Thomson coefficient's negative, indicating it comes out hot. This is one of these crazy cases where, hey, some fluid, you go through a throttling valve, no change in temperature. Go through a throttling valve for some, it's really cold. Go through a throttling valve for some, it can be warm. And you know what? For the same fluid, you can have all three cases. For the same fluid, we're going to talk about nitrogen now, okay? We'll get all three behaviors the same. Okay, so here's a plot to help us understand the Joule-Thomson effect or the Joule-Thomson coefficient for the fluid nitrogen. When you approach a problem like this or a plot, first try to dissect it. It's only for nitrogen, right? What's on the x-axis? Entropy. Entropy, you know, is a value of 3, 4, 5, 6. You don't make heads or tails out of that. It's just in value for entropy. What about the y-axis? Temperature, what's it go from and to? Well, down here is 70 what? Kelvin? Cryogenic temperature. It's very cold. And then 300 Kelvin, what's that? Room temperature. So we're covering a large range of temperature. Now, can you see the dome on this? And what's this point right here on the dome? The critical point. So everything, this black curve over to the side, what is that showing? A state's saturated, all saturated, vapor, all saturated, liquid. Underneath the dome, it's two-phase mixture, right? So yes, you can get liquid nitrogen. You can have nitrogen. That's the majority of what's going in and out of your lungs right now. You can get it so cold that you can liquefy nitrogen. True? Notice what is the temperature for liquid nitrogen. What is the critical point for nitrogen? Around 126 Kelvin. They have a line of constant pressure. See that? 20 kilopascal, 100 kilopascal, 1 megapascal, all the way up to 100 kilopascal. So these blue lines swooping down are lines of constant pressure. Why is the 100 kilopascal thicker? Because it's atmospheric pressure. And 20 kilopascal, we'd say it's a vacuum. What other lines of constant H? Look at here, the red lines. They're constant enthalpy, aren't they? So what do the lines of constant enthalpy do? What do they look like out in this region? Flat. Constant. Yeah, right? Not a function of S. Just a function of temperature. This is ideal gas behavior way out here. Really way out here, okay? It's up hot and low pressure. All right? But a lot of region, the enthalpy is not just a function of temperature, it's a function of temperature and pressure, true? So where would that be? Everywhere where it's not a function of temperature only. So this is out in the real region, real fluid region. So this region in here, real gas. How about if I said down in this region, what is the description of that fluid, that nitrogen over here? Subcooled liquid, that's right. And then really this is all supercritical up in here. Real gases and supercritical behavior. Okay. So let's go ahead and pick a point. Let's get a pressure of 5 megapascal and a temperature of 255 Kelvin. 255 Kelvin. And it just happens to be right at this intersection of this red line and that blue line at that point. Let's say that's the inlet, state 1, to a throttling process. And it throttles down to a pressure of 100 kilopascal. So it's going to end on the line of 100 kilopascal. So there's state 1, that's the inlet to the throttling process. Where's the exit to the throttling process? Where is that on this diagram? It has to be somewhere on the thick blue line. Is it going to be just straight across, hit there? It'll be on the intersection of the red line because the red line indicates constant enthalpy, and we know the throttling process is isenthalpic. So we do see that there is a temperature drop in this process, and it looks like it comes out around 250 Kelvin or so right here, 250 Kelvin. Hence, there was about a 5 Kelvin temperature drop in that throttling process. Was there a whole lot of cooling? No. No, not at all. Let's take a look at another case, though. Let's say the nitrogen was at that same pressure, 5 megapascal, but this time, let's say the temperature was 125 Kelvin. 125 Kelvin. Find that spot. Where is that going to be on the diagram? So it's right about the same temperature as the critical point, and it's about right, let's see, about right here. All right, maybe not on that red line of zero enthalpy, because the enthalpy is negative 50, then negative 100, but let's say it's on that red line. Okay? If I undergo the throttling process, same pressure change, I'm starting at 125 Kelvin. What is the temperature at 100 Kelvin after the throttling process? It goes right here, down to there. That's state 2, state 1. And we find that it's very cold. What is it? Maybe around 77 Kelvin. 77 Kelvin. That's what we call the boiling point for nitrogen at atmospheric pressure. The 100 kPa, boiling point, 77 Kelvin. So we see it really is cold. That's what we'd often expect coming out of vapor compression refrigeration. We studied vapor compression refrigeration. That's what we do. We like to drop it into the two-phase region and then boil. If I look at this point right here, it's on that thick blue line. What's the quality visually? What's the quality at that state? Just visually guess. 60, 65, right? So that means 60% is already in the vapor state, leaving 40% of the mass ready to boil and provide a lot of cooling if at 77 Kelvin. True? All right. Now, think about it. Our goal maybe was to get something nice and cold on the outlet. And so we come in with P1, T1. We drop it to P2, and we want T2 as low as possible. As low as possible. For the first case, it seemed like a dismal failure. Same pressure. The second case, it looks pretty good. True? What could you replace instead of having a restriction, instead of a throttling device right here? Let's say you propose, you're an engineer in your company. I propose something else, not a throttling device. I propose we put this in there to help, especially for that first case, to get a very low temperature out. What would you put in there? Get rid of the throttling device. What would you put in there? You still have the same pressure in, same pressure out. Same temperature in, but you want temperature out too to be very low. Put a turbine in, right? What's the turbine going to do? It's going to convert some of that flow energy or enthalpy into some shaft work going out, and I'll do something else with that shaft work. I'll hopefully do something good with it, but as long as I get it out of the nitrogen, right? So if I put in, let's say, a turbo expander right here, just here's my illustration of a turbo expander, right? I'm going to extract some power out. Do you think I'm going to have any Q dot into it? Turbo expander? No, it's probably going to run adiabatically. No heat transfer. Shaft power out. Changing kinetic and potential energy, negligible. So what about the second law analysis? Where would I find the good state 2 if I ran it through that turbo expander? Oh, it's still going to that thick blue line of 100 kPa. Where would I find the, instead of state 2 being right here, where is state 2 possibly going to be? It's isentropic. If it's isentropic, reversible, the best turbo expander you could design. Reversible, adiabatic, it's isentropic. What about that outlet temperature? Where's it going to be? Is there a big difference in the temperature now coming out versus the previous case? A huge difference, true? That's why they have turbo expanders in cryogenic refrigeration applications. You can see it right here. Let's say you don't have a really good turbo expander. Let's say its isentropic efficiency is not 100%, which is shown right here, but it's 80%. Where would state 2 be then? It would be over here somewhere. Oh, I'll still take it. You know, the isotropic efficiencies of some of the first turbo expanders, I think, were in the range of like 30% or 25% isentropic efficiency, which means they probably were kicking over here, which is still a whole lot colder than before, just putting it through a restriction. And then they kept improving and improving and improving because you can get it so much lower temperature. Is this still a gas coming out of state 2 over here? It's all a gas. Oh, it's a cold gas. It's probably not behaving as an ideal gas, but it's still a gas. And so it's better to expand a gas through a turbo expander than try to do it for the second case where we started here. Think about this one. If we start here, do you think you're going to get a tremendous advantage for the turbo expander? What would if you could make a turbo expander like that, right? Because you're going to start to expand something that acts almost like a liquid. Look at where state 1 is. And then you're going to go into two-phase region, and guess what? Your temperature out versus your temperature out before, they're the same temperature out, 77 Kelvin. Oh, you still have more liquid to vaporize. But in this case, the turbo expander is not as valuable. The first case is huge. Can you see that? Even a poor turbo expander would be great. All right. Where do we find the Joule-Thomson effect for cooling? Well, you just do a quick search and you can find these things. Before they had good turbo expanders, they did just a lot of Joule-Thomson expansion for cooling and even did it to get down to cryogenic temperatures. It was tough. It was really tough. Okay, but they did it. But then as soon as they could make some poor turbo expanders, they introduced them and left the Joule-Thomson behind. But when you're in the world of small things, miniature micro refrigerators, okay, and you can sometimes just continue to use the Joule-Thomson coefficient to get things cold. So if you have a bottle tank of nitrogen, right here, they're showing that, going through a filter, there's a micro refrigerator, and you can have very, very low temperatures in the spot locations. Okay? Now, it's a lot better if you can somehow cool the nitrogen at high pressure and then expand it. So maybe put in a vapor compression refrigeration system to cool it, then expand it, right? Just go back to this diagram here. If I can cool this some at high pressure, I'm going to have a lot better effect of the Joule-Thomson coefficient as I go through isenthalpic expansion. So the American Gas Association has a glossary of terms, and so if you take a look at it, they have a whole thing on Joule-Thomson coefficient. It says the Joule-Thomson effect is the cooling which occurs when a compressed gas is allowed to expand in such a way that no external work is done. So they're not doing the turbo expander. No external work. It's also, there's no heat transfer. So Q dot's equal to 0 and W dot's equal to 0. And they say the effect is approximately 7 degrees Fahrenheit per 100 psi for natural gas. So what is natural gas primarily? What component? Methane, CH4. So if you have a pipeline of methane, and there's lots of pipelines of methane, and you have a valve, and that valve is partially closed, it's a restriction. And maybe you come in here with, 1100 psi. And it drops down on the back side of the valve to 100 psi. All reasonable pressures. So what's the delta P? It's 1,000 psi pressure drop, right? They say that there will be a 7 degree Fahrenheit drop for every 100 psi pressure drop. If this is coming in at, let's say it's coming in at 100 degrees F, what's the temperature drop if the pressure drops 1,000 psi? 70 degrees F. What is the outlet temperature? Where does water freeze? 32. So a lot of times you only have 70 degree F natural gas flowing. You could get some very cold natural gas. And if you have just a little bit of moisture in it, which they try to get rid of, they really limit the amount of water vapor you can have in natural gas, then you can have problems because what will you have over here? Ice or some molecules acting like ice, and they could build up. Let's say you close that valve down, but it wasn't completely closed. A little bit's going through, and a little bit of water in it. Guess what could happen? It starts to deposit that water right there and build up ice, build up ice, build up ice. You decide to go open it, and you don't get the flow you got because it's plugged. Plugged with ice. It does happen, has happened. So this is one of those interesting applications. Let's see about understanding this with the temperature entropy diagram for methane. So again, methane, CH4, the primary component of natural gas. Okay. So we have the temperature. What do we have here? Degrees F. Maybe it's a little easier for us to understand. And then we do have entropy. It doesn't matter what the units are. It's pretty abstract, but it's in BTUs per pound mass degree R. What is this point right up here? Critical point. What's the temperature for methane's critical point? It's around negative 116 degrees F. All right, and the pressure is around 673 psi A. So that right below the 700 psi line, the critical point pressure. The thick blue line around 14.7 psi A atmospheric pressure. This is below atmospheric pressure. These are 100, 300, 700, 1500, 3000, and 7000 psi. So those are, for the red lines, those are constant enthalpy. Let's pick, let's say we have, I don't know, 100 degree F at some pressure, 1500 or somewhere in there, right? And you want to drop it down to this pressure. You're going to follow a line that's red, and I know I didn't have one that intersected there, but you can see that you could have that temperature drop that would cause ice up or ice building. Let's do this. We'll do a little work in Excel. I'm going to do this. I'm going to type methane, and that'll be the gas that I use. And what I'm going to do is I'm going to talk about different states. State 1, and then I'm going to go to state 2, where I'll talk about the pressure, PSI, and the temperature in degrees F. What did we want to start at? 1100 pressure, and maybe drop it down to 100 PSI, right? And what temperature do you want to start at? 70 degrees F. Okay. And let's call and get the enthalpy in BTU per LBM. And here we're going to have to use Refprop, enthalpy of that gas. Now I could type that gas or just say go get it from this cell, A1, and if I want to always keep it at A1, then what I'll do is I'll put a $sign and a $sign. So it's always going to go to A1 for the name. Okay, the next thing is I'm going to evaluate as a function of pressure and temperature, English units, and the pressures in this cell, comma, temperatures in that cell, and I know those are the right units that this code likes, and so there's a value for the enthalpy. I undergo an isenthalpic expansion to the next lower pressure, and now I want to know, this one the pressure and the temperature fixed the state, this time the pressure and the enthalpy fixed the state. So I say give me the temperature as a for methane right here, $, okay, knowing pressure and enthalpy. Oops, that was I think I'm not supposed to have that there. For English units and that value of pressure, I have to grab it and scoot it in. Cell E4 has my enthalpy value. And take a look at that temperature. It's dropped down to 11.8 degrees F. That's way below 32, right? So what was the change in the pressure? That's just this pressure minus that pressure. So it was 1000 psia. And what was our change in the temperature that we measured? It's equal to, it started at 70, ended at 11.8. So it was a 58.2. So my Joule-Thomson coefficient approximately is so many degrees change per psi. So it's about, this is how many degrees F per psia, right? That's not so pretty because it looks like that. So what I want to do is I want to report the Joule-Thomson just like the Natural Gas Association did in that many degrees, but it's per 100 psi. So it's in degrees F per 100 psi. See the difference? So it looks like these values are coming in right at 5.8. What did it say? It was around 7, right? So it's close, but it's not spot on. In their glossary, it said it was around 7 degrees F per 100 psi. What you can do is start changing things. Let's say it went from 300 psi to 100 psi. Well, that's now 5.6. Also, this software can get the Joule-Thomson coefficient. It's equal to JOU. There, it helps you remember what you're looking for, so hit Tab to finish it. The Joule-Thomson for methane in cell A1 as a function of pressure temperature, English units, this value of pressure, this value of temperature, and it reports it to 0.054. If you wanted a Joule-Thomson in the other units where it's degrees, no, let's just put F per 100 psi. You just take that value and multiply by 100, and you can see it a little clearer, right? So these values of Joule-Thomson coefficient are pretty close to this value right there. It's actually in between. 5.6 versus 5.4, 5.8. That makes sense? So this quick check with Refprop in Excel confirms what we expected. All right. Thank you for your attention. We'll see you next time.